Right, so I'm ready now to do question 6 of the PHY101A paper from 2013-14, a relativity question all about events and world lines and Lorentz transformations between X and CT. So material from close to the beginning of the course. So two events occur at times TA of 0 nanoseconds and TB of 3 nanoseconds in the unprimed frame, and at positions XA of 1 meter and XB of 2 meters. So to do this question I would immediately start drawing space-time diagrams. So if you remember, a space-time diagram has displacement on the horizontal axis and the velocity of light times time on the vertical axis. Now it says in the question that event A occurs at a position 1 meter and event B occurs at a position 2 meter. So I'm going to subtract 1 from both of those numbers and put event A at the origin here, and I can mark it event A, and event B is at a position relative to A of 1 meter. So this is x equals 1 here, and this is x equals 0. There's nothing wrong with subtracting the same number from all the x coordinates of all the events. As long as you're consistent between different events, that's fine. And it's just going to make it easier to derive the equations of world lines, which we're going to have to do in this question. Okay, so event B occurs at some time later in this coordinate system. Right, so we're going to put its time as positive and its position as positive as well. And so this is event B up here. Now what are the coordinates? Well, I've got the coordinates of A as being 1 meter and 0 nanoseconds, but I've subtracted 1 meter. So I'm going to write the coordinates of A as 0, 0, and the coordinates of B, well, it's at a position of 1, it's at a position of 1, so X is 1, and CT, if T equals 3 nanoseconds, then CT equals 3 times 10 to the 8 meters per second times 3 times 10 to the minus 9 seconds, and that equals 9 times 10 to the minus 1 meters, or 0.9 meters. So that's event B. That's the CT coordinate of event B. So this coordinate here is 0.9. So the coordinates of B are 1, 0.9. So those are my two events on the space-time diagram. So now I've done that, I can start answering the question. So part A, are the events space-like or time-like separated? Now if you remember from the course, when I talked about past, future and elsewhere, the definition of space-like separated was that events that are space-like separated are not causally connected. What does that mean? It means that some physically allowed world line can connect the two events. In other words, one can exert a causal influence on the other. If that's not true, then you can't have any signal propagating from one event to the other, and therefore there can't be a causal relationship between them. So what's the fastest thing which can fly out of event A? Well, the fastest thing is a light beam. And a light beam from the origin, which is where event A is in my coordinates, has the equation CT equals X. In other words, on a CT x-axis, the light beam has, the world line of the light beam has slope +1. Right? Starting here has slope 1, going up there, that's the world line. Now, when it gets to a CT coordinate of 0.9, in other words, the time coincident with event B, its x coordinate is also going to be 0.9 because the line has slope 1. Right? But we know that the x coordinate of B is bigger. It's 1. So that means that event B cannot be reached by the light beam starting at event A. Therefore, the two events are not causal contact. Therefore, they are space-like separated. So the one-sense justification is that there is no world line which can causally connect events A and B. Therefore, they are space-like separated. So that's the answer to part A. There are other ways of expressing the answer, and if you're unsure about your way, you can email me and ask. Part B. How fast and in what direction must a prime frame be moving with respect to the unprimed frame for the two events in the prime frame to occur simultaneously? So that's a matter of applying the Lorentz transformations. So we know the coordinates of event A are 0, 0 in the unprimed frame. Now the Lorentz transformations are this: Ct prime equals gamma Ct minus beta x, and x prime equals gamma x minus beta Ct. So if x and Ct are both 0, then x primed and Ct primed are both 0 as well. So in the primed frame, the x and Ct coordinates are still, the x primed and Ct primed coordinates are 0, 0. Right? And these are Lorentz transformations. So event B, in the unprimed frame, the x and Ct coordinates are 1, 0.9, where x is the 1 and Ct is the 0.9. But event A in the primed frame occurred at a time of 0. So our criteria for the two events being simultaneous in the prime frame is that event B also has to occur at a time of 0. In other words, Ct primed B has to be equal to 0 for simultaneity. Right? We can substitute that into the Lorentz transformation and write that 0 equals gamma times Ct of event B minus beta x of event B, which implies that Ctb equals beta xb, or beta equals Ctb over xb, which equals 0.9 over 1, so that beta for the two events to occur simultaneously has to be 0.9. So the answer to this question is that your prime frame has to be moving in the direction of increasing x, because remember that these Lorentz transform formula assume that the primed frame is moving in the direction of increasing x with respect to the unprimed frame, and it has to be moving at a velocity of 0.9 of c. Right. Now, in the preamble, it says that both events occur on the x-axis, and then it says source position from these events emit light beams directed in opposite directions, so that the light beam from event A is travelling towards event B and vice versa. In part C, you're asked to draw a space-time diagram for that. So, some redrawing is required. We have, in the unprimed frame, an event at 0, 0, and another event at 1, 0.9. This is Ct. This is x. Always label your axes. This event emits a light beam. So the world line of a light beam is at 45 degrees, and the equation of the light beam is Ct equals x, because it's emitted at the origin. Now, event B also emits a light beam. It goes in the opposite direction. So this light beam, going that way, the angle of that with respect to the direction of increasing x is 135 degrees. So it's moving at 45 degrees but in the opposite sense. So that angle there is actually 45 degrees. And so this line here has slope -1, whereas this one had slope 1. Right, now the equation of, we'll call this line A, the one that's travelling in the direction of increasing x, the equation of line A I've already written down. It's ct equals x. Now line B has a more complicated equation because it doesn't go through the origin. So here you need the formula for the equation of a straight line. Now usually undergraduates know this formula. Y equals mx plus c. However, in this case, the vertical axis, well in this case we don't have an intercept with the vertical axis, which is what c is. Instead, we have a point that we know that the line goes through. It goes through the point 1, 0.9. You can also show, and you should know this, is very useful, that another equation for a straight line is y minus y1 equals m times x minus x1, where y1 and x1 are the coordinates of a point the line passes through, any point. Coordinates of any point on the line. And y is, as usual, the vertical axis, and x is the horizontal axis, and m is the gradient, or the slope. So we can write the equation of line B. All we have to do is replace y by ct, replace y1 by the y coordinate of the point we know it goes through, which is 0.9, replace m by the slope of the line, slope of line B is -1, and replace, well x is still x, and replace x1 with the x coordinate of the point we know the line goes through, which in this case is 1. So that, ct minus 0.9 equals -1 times x minus 1 is the equation of line B. Rearranging the equation, you get ct equals 0.9 minus x plus 1, because the -1 slope multiplies by the -1 in the bracket to give you +1, or ct equals 1.9 minus x. So that's the equation of line B. The event of them intersecting, which you should also put on your diagram for full credit, because you were asked to, is found by solving the equations for line A and line B simultaneously, because they're only simultaneously true at the point of intersection. So if we take this ct from the equation for line B and we substitute in for x, you get x equals 1.9 minus x. That's an equation for x. So 2x equals 1.9, or x equals 0.95. But because x is 0.95, and because of the equation of line B, x equals ct, that means that ct equals 0.952. So the coordinates of the point of intersection of the two light beams are 0.95, 0.95. And that's the answer to part D of question 6.